Bismillahirrahmanirrahim. Assalamu alaikum, dear student. We were discussing about the dynamic mechanical analysis of thermosetting materials in thermal analysis. And so far, we have discussed some of the important aspects of the said topic, which includes the two-dimensional actually representation of thermoset cure and the macroscopic development of rheological and mechanical properties during network formation, and the, we have also compared and discussed some of the important thermal analysis technique, which includes the diffraction scanning calorimetry, TMA thermomechanical analysis, and thermogravimetric analysis TGA. And we have discussed some of the important principles regarding the characterization of these techniques of unknown for the unknown samples. Moreover, we also studied some of the storage modulus and about loss modulus and tan theta. And now we would like to talk about the dynamic mechanical analysis of lightly and highly cross-linked thermosets. In figure 5, it illustrates typical dynamic mechanical analysis of cured thermosets. There are three regions: a glossy region, which is similar for all thermosets and is further characterized by very high storage modulus, which is less than 1 GPa, low loss modulus, and very low tan theta. A glass transition region where the storage modulus can decrease by a factor of 10 to 100, and the loss modulus and tan reach maxima. A rubbery plateau region with stable storage modulus proportional to the cross-link density and low loss modulus and tan theta. This is the figure 5, which actually schematic description of dynamic mechanical analysis of highly and lightly cross-linked thermosets. For fixed frequency, dynamic mechanical analysis may be performed in single cantilever, dual cantilever, 3-point bend, tensile, or shear sandwich deformation modes. Two illustrations are shown below. The first, shown in figure 6, is a single cantilever mode. Neat sample can be made in Teflon or silicon rubber molds and are generally 0.5 to 2.5 mm thick. The question may arise in your minds that why we need to use Teflon or silicon rubber molds. The use of Teflon is quite imperative and quite useful in different autoclaves for sterilization and even for the hydrothermal synthesis of many inorganic organic hybrid compounds. This is due to the very resistive nature of Teflon towards most of the chemicals. The chemicals may be the hard acids, bases, or even different corrosive components. Teflon have high resistivity and non-reactive nature towards these acids, bases, and different carcinogenic chemicals. So, it is believed that the Teflon, which is lined in an stainless steel autoclave, might be helpful for the successful synthesis of desired compounds without impurities, because if the reactants, which may be the acids or bases, have affinity with the wall of container, the container wall, then there is might possible that impurities may incorporate in our products. So the use of Teflon lining is quite important for the uh, impurity free products, and it usually uh, zero point 0.5 to 2.5 mm thick. This method can be quantitative if the dimensions are precise, but it requires length correction for the clamps. For very high modulus samples, the 3-point bend mode may be preferred, which has the additional benefit of eliminating clamping effects. And here we can see that in figure 6, single cantilever mode for dynamic mechanical analysis, in which we can see we can put the sample over there with, there is a stationary clamp which is not movable. The second one is a movable clamp, and we can move that clamp upward and in downward directions. The second method illustrated is the wire mesh method, which is done on the tensile mode. The wire mesh is usually stainless steel and of approximately zero point 0.1 mm thick, which may be easily coated with a liquid or paste material. The thickness is uniform and may be varied by using different thickness of mesh. Because the mesh sample is mounted on a 45-degree bias, where the mesh itself has almost no shear resistance. This technique gives a very sensitive measure of glass transition. Semi-quantitative values G dash and G double dash for may be extracted via composite analysis. Sample spotted on metal shim or glass fabric are normally analyzed in the dual cantilever mode. And in figure 7 we can see that wire mesh technique for dynamic mechanical analysis of liquids and paste. And we can see that there is a stationary clamp which is unable to move, while there is a mesh between the stationary clamp and movable clamp. Moreover, gelation is the first appearance of a cross-linked network. It is the irreversible transformation of a liquid to a gel or rubber that is accompanied by a small increase in the storage modulus. A distinction may be drawn between molecular or chemical gelation. This is actually the phenomenon, and macroscopic gelation. This is actually the consequence. Chemical gelation is defined by Flore is the approach to infinite molecular weight. It is an isoconversional point that is observable as the first detection of insoluble cross-linked gel in a reacting mixture. The reacting mixture might be known as Sol. Chemical gelation is also defined as the point where tan theta becomes frequency independent. Macroscopic gelation may be observed as the approach to infinite viscosity. The first evidence of an equilibrium modulus, the G dash, which would be equal to G double dash, crossover in a rheology measurement, or as a loss peak in fiber and mesh supported systems. And this is actually the second method which illustrated the wire mesh method, and it is done on the tensile mode. The wire mesh is usually stainless steel with an approximately zero point 0.1 mm thickness, which may be easily coated with a liquid or some paste material. The thickness of this stainless steel wire mesh is supposed to be uniform and may be changed by using different thicknesses of mesh. Samples spotted on a metal shim or glass fabric are normally analyzed in the dual cantilever mode. As just mentioned, the gel point is often estimated in a rheological measurement as a crossover where G dash is equal to G double dash or tan is equal to 1. This is actually depicted in figure 8 for 5-minute epoxy. In this material, the 5 minutes refers the gel point or maximum work life at room temperature. The value measured can be seen to be very close to this time. As mentioned earlier, a better measurement is the point where tan theta becomes frequency independent, which is usually close to but not necessarily equal to 1. Note that a rubbery plateau modulus between 10 power 5 and 10 power 6 Pascal is created, and it's reached after long times, demonstrating that vitrification that would result in a modulus less than 1 GPa did not occur in this sample. This figure 8 is actually the dynamic rheology of a 5-minute epoxy showing measurement of gelation. Vitrification is the gloss formation due to glass transition increasing from below Curie temperature to above Curie temperature as a result of reaction. We people should aware about the Curie temperature first. As we have discussed earlier in phase transition lectures that Curie temperature is supposed to be the temperature at which a crystals or compound exhibit different structures. The temperature below which the structure of a compound is changed is the low temperature phase, and subsequently the temperature above which the structure of a material is uh, order or highly disordered is a high temperature phase, and both the temperatures, both the structures have different parameters above and below the Curie temperature. This is actually the particular temperature at which the crystal actually shifts its structural parameters and change into different structural parameters. Most of the time, the phase transition when phase transition occurs in a compound, the structure which is actually above the phase transition point is known as high temperature phase or HTP. The high temperature phase usually exhibits that the sum of the atoms, sometimes the terminal atoms of molecules, have highly disordered vibrational motions in their molecules. So, due to the highly disordered vibrational motions of the atoms, especially the terminal atoms, would yield the phase transition in that compound. While if we talk about the below phase transition point or below the Curie temperature, the structure may exhibit that it it have low temperature phase. The low temperature phase is actually the phase in which the disordered atom of the molecules becomes ordered. Due to the shifting of this orderness and disorderness in a crystal actually creates a phase transition, and the point at which both phases are shifting each other is actually the phase transition point, or the sometime Curie temperature of that particular component. Vitrification is glass formation due to the glass transition increasing from below Curie temperature to above Curie temperature as a result of reaction. It only occurs when Curie temperature is greater than glass temperature. And what would happen if the Curie temperature less than the glass transition temperature and begins when glass transition temperature is equal to Curie temperature? The definition of vitrification is actually the glass transition temperature when equals to the Curie temperature. There may or may not be more than one Curie temperatures or glass transition temperatures in any inorganic compound. We know that if a molecule, if a inorganic material exhibits more than one Curie temperatures, then it would be easy to classify different Curie temperatures or glass transition temperatures with alpha, beta, gamma, etc., to indicate that this would be the first glass transition with alpha, the second glass transition would treated as beta, and third glass transition may treated with gamma. These symbols are quite helpful for the better understanding of different glass transitions in compounds. Moreover, vitrification is actually the glass formation due to the glass transition increasing from below Curie temperature to above Curie temperature as a result of reaction. Moreover, it only occurs when Curie temperature is less than glass transition temperature and begins when glass transition temperature would be equal to the Curie temperature, which is actually the definition of vitrification. Vitrification is reversible by heating, which means that liquid or gel change into glass, and glass may subsequently change into liquid or gel. It causes a dramatic showing of the rate of cure as a result of a shift in the reaction from chemical control to diffusion control. Vitrification is mechanically observable as a large increase in modulus and frequency dependence, and it would the dependent loss peaks. This phenomenon is illustrated in the following slide. It is observable by MTDSC as a step decrease in heat capacity. This is all about this lecture. Thank you very much.